Hey folks, welcome back. My name is Mr. Kim, and I will be going over this time the June 20th Chemistry Regents exam from the year 2024. Let's get started. 51. Compounds that contain element boron, such as boric acid and sodium borate, produce green flame when the sample of one of these compounds is placed in a laboratory Bunsen flame. If this flame is viewed through a spectroscope, a bright light spectrum is seen. 51. State how the bright light spectra of known elements can be used to identify unknown elements whose bright light spectrum was viewed through a spectroscope. This is a lab that we did in the beginning of the year where you look through the different emissions, right? So how does that work? We know you remember from the lab that any of the different elements that you saw had a distinctive light, color, and if you look through a spectroscope, you saw a specific lines under the certain spectrum, right? You guys remember me making you use color pencils to draw that? So the answer would be that bright light spectra or spectrum, lies a plural, are specific to each element. The spectra of the unknown element can be matched to each of the known elements. Okay, that's supposed to be a period. All right, let's continue. 52. State in terms of electrons and shells why the electron configuration 221 is excited state electron configuration of the boron atom. All right, so the best way to start this is to actually go look at a ground state configuration of boron. If you don't know, you can look it up, right? It's right here. You go over here, the ground state configuration of boron would be 2-3, right? So we know that ground state electron configuration excuse me, of boron is 2-1. Therefore, 2-2-1 means an electron from which shell, guys? What do you think, right? Over here, which would be second shell, has jumped up and created a third shell. Okay? All right, let's continue. The silicon is an element in group 14 in the periodic table. The atomic mass and natural abundance for the three naturally occurring isotopes of silicon are shown in the table below. Draw the Lewis electron dot diagram of the atom of silicon in the ground state. So again, let's highlight some of the things. Electron dot diagram for silicon and in ground state. So I'm going to go to here, look for silicon. Silicon in ground state, right, has a 2-8-4. And remember, Lewis diagram shows number of valence electrons, right? So not only that, silicon is in the same family as carbon, and then you know what a carbon looks like, right? So over here, you're going to draw silicon, And silicon has 4 valence electrons, so you're going to draw Si with 4 electrons. Now, the proper way to do it would be the first 2 electrons are always paired together, and then the next 2 are like so. Or, in the case of Regents, they will also be willing to accept something that looks like this, right? But I would try to stick to drawing it this way. Remember, the filling order is 1 and 2 together, and then 3, 4, 5, 6, 7, 8. Remember that. 54. Compare the energy of an electron in the first shell of a silicon to the energy of an electron in the third shell of the same atom. All right, what do we know? We know that as electrons move further away from the nucleus, it's at a higher orbit, right? So we know that it's at a higher energy level, right? That has to do with the electron, the bright light spectrum, right? So in order to answer that, what do we know? The electron and then in the end, it doesn't really matter which way you start, but let's just look at, they said compare the energy of electron in the first shell to the third shell. So first shell, electron has, now remember, it's lower, right? It's a lower orbital, so therefore has lower energy. Than the electrons in the third shell of silicon. Okay. Number 55, show a numerical setup for calculating the atomic mass of element silicon. Remember, it's the sum of the atomic mass times its natural abundance. So I'm going to try to remember this. This is the third FRQ, and they're making us do this for the third time in a row. So it's pretty important that you know how to do this, right? So, and it says, once again, they want the numerical setup. They don't want the answer. You write the answer and you don't put work, you're going to get this wrong. So let's go. It's 2798. So 27.98 times the percentage as a fraction or a decimal is 0.9222. 0.9222 plus the second one is 2898 times 0.0469, right? 0.0469 plus 2997 times 0.0309. 0.0309. The other thing I need to tell you is that when you when you write this, please make sure your decimals are clearly visible and that you didn't just put a little dot that is not visible. Make sure your decimals are visible. Okay. All right, let's go. 56. The unbalanced equation below shows a reaction between nitrogen monoxide gas and oxygen to produce nitrogen dioxide gas. State in terms of reactants and product why this reaction is synthesis reaction. Well, what do we know about synthesis? By definition, synthesis means what? You start with two simpler things, and then you create one more complex thing. So that's literally what we're going to write, right? Two simple things combine to form one complex thing, right? Now remember, in this one, they want you to understand the definition, right? They want you to regurgitate the definition of the reactions. So right now is a good time for you to go review and remember the 5 different types of chemical reactions and remember their definitions so that you can regurgitate it should they ask you, like 56. 57. Balance the equation in your answer booklet for the reaction using the smallest whole number coefficients. All right, remember what I said. You should be able to eyeball balance at this point, right? Let's go. So you got one nitrogen on the left side, one on the right side. Nitrogen looks okay. Let's look at oxygens, right? Remember what we said. When you have something like O2, touch that last, right? So what do we got going? We got 3 oxygens total on the left side and 2 on the right side. So the only way to make this happen is what? You can multiply this NO2 with any other number, and you'll know that this 2 will only be an even number, right? Because 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. So therefore, if I multiply this by 2, what happens? I understand that on the left side, you can't have an odd number, so you got to have an even number. So if I do that, what happens? Nitrogens are balanced, and what you end up with is 4 oxygens on the right side, 4 on the left side, and we are balanced. 57. No, 57 is done. That's why I actually tell my students to cross it out, but I forgot to do that. Determine the percent composition by mass of oxygen in the product NO2, whose gram formula mass is 46 grams per mole. So it's NO2, right? So it's a percent by mass. And I think the equation, if you don't know, might be in here, right? Let's see, right? Percent composition is right here, right? It's the mass of part over mass of whole. So let's say NO2 is what we're looking at. So they want oxygen, so it's mass of oxygen over mass of NO2, right? That's how we would do it, right? So let's go figure it out. Oxygen is what? Oxygen is 15.9994, right? Remember? Because, oh, too much. Go back. Oxygen is 15.9994, right? So I'm going to write that down. So in order to calculate this, it's going to be 15.9994 is the oxygen all over NO2, right? So I'll write that down here. You don't have to, right? Times 100, right? Don't forget the 100. Okay, so the whole is what? You can figure it out, but they actually gave it to you right here, 46 grams per mole. So it's 46 grams per mole. And what does that come out to? I think that comes out to, I'm sorry, I screwed that up, right? Because it's how much oxygen? There's 2 oxygens in here, right? So it's going to be 2 of these, right? Right? Because it's not that it's O2, but it's that in NO2, a total number of oxygen is 2 in there, okay? So you gotta put that in. So when you do that, what do you end up with? You should end up with, I believe, 69 point something, and with the sig figs, you'll get 2 sig figs, and the answer should be 70%. All right, let's continue. 59. The ionic radii of group 17 elements, right? So group 17 is what? Halogens, right? Are given in the table below. Identify the noble gas that has atoms in the ground state with the same electron configuration of Br minus. So there's a couple of ways to do this, right? You can actually do the electron configuration, right? What's Br? Bromine is right here, and it's 2, 8, 18, 7. And remember, why did they end up making ions? Because they want to get to an octet. Well, it's a Br minus. That means that it has gained, right? Extra electron, right? Which means what? The ground state of bromine is 2, 8, 18, 7, right? Except since you're adding another electron, your state should now be 2, 8, 18, 8. And that's what we're looking for. And who's that? That's krypton, right? So that's literally what you're going to write, Kr, or write in krypton. All right, let's go. Oh, that's 60, right? I'm sorry. Should I? Oh, that's correct. That's 59. All right, let's go to 60. In state in terms of electrons, why the ionic radius of group 17 element is larger than the ionic radius of the same element. All right, so let's take a look. Ionic radius of a group 17 element, right? Ion, right? Remember, this is halogen, right? which are what? Which are these guys over here, right? These guys over here. So what do we know about halogen? They all tend to have a tendency to form anions, right? Anion is especially of the -1, right? Charge. So what do we know about anions? Well, anions are holding an extra electron for the same number of protons, right? Right. So, for example, if you look at fluorine, right? Fluorine has 9 protons and 9 electrons, but fluorine minus would have 9 protons, but it has 1 extra electron, right? So therefore, what happens? You guys remember the dog walker analogy? I said the nucleus is you, and then you're trying to walk the dogs. So if you have extra dogs, they spread out further, right? Because it's kind of harder to hold on to all of them. So then, really, in the end, the answer would be what? Group 17's ions. You got to first state what kind of ions they are, because there's 2 types. There's cations and anions, all right? Are anions, right? Meaning what? Meaning they have extra electrons than their atoms, right? So this will make it harder for the nucleus of the anions from holding onto their electrons. Okay. All right, let's continue. So 60's done. Letter 61. The diagram below represents 2 sealed rigid containers and the conditions of pressure, volume, and temperature. I know that, but like I said, putting the letters in the problem starts to make them pop out to your eyes, and you start having some idea on what topic we're supposed to be talking about. Container A is filled with N2 and container B is filled with O2, all right? Explains terms of strength of intermolecular forces. Remember, that's how strongly the particles are pulling or onto each other. Why the gas in container B at standard pressure has a higher boiling point than the gas in A at a standard pressure. All right, so they're both at standard pressure. So they're saying that why does a gas B at the same condition have a higher boil temperature, and this is a lower boil temperature? All right, so what does it tell you? That tells you that who's easier to boil off? Boiling off is when you're kind of breaking them apart and chucking them into the air as a vapor, right? So therefore, who's easier to boil? The ones that aren't holding onto each other so tightly. Am I right? So therefore, if they're not holding onto each other so tightly, that would mean that they would boil. It won't take so much temperature to boil them up. So therefore, at a lower temperature, it'll already start boiling. So therefore, in comparison of the intermolecular forces, you understand that container A, because it boils at a lower temperature, right? They're kind of weakly attached to each other. So therefore, we know that it's like this. Okay? So that's what we're going to say. We're going to go to 61, and we are going to say in 61, gas B has a stronger intermolecular force. Okay. That's not molecular. Molecular force. You could also conversely say gas A has a weaker intermolecular force, and you'd be just as correct. Let's go to 62. In a space in your answer booklet, state a numerical setup for calculating the pressure if the gas in container B is cool to standard temperature. All right, so that means what? We're looking at B only, okay? We're looking at B and B only. What does that mean? Then we got pressure initially 101.3 kilopascals. Volume is 750 milliliters. Temperature equals 298 kelvins. And then we want to, right, calculate the pressure, right? If it's cool to standard temperature is what? If you don't know, you should know this, right? But if you don't, where do we go? We go to the front, where the standard temperature is right here, right? So it'd be 273 kelvins. Now, because it didn't say anything here, you assume that the volume is still the same, right? Remember, this is a gas law problem, right? So this is condition 1, and that would be condition 2. And this is our shopping list, right? All right, so now what? If you don't remember the equation for combined gas law, it's PV over T equals PV over T. Then it's here somewhere. There it is, right? PV over T equals PV over T, okay? So that's it. So now all we have to do is just plug these values in, but we're going to set this up properly, right? So I know we got, they're trying to say calculate the pressure, P2, right? Right? Pressure is, I'm going to leave that as alone, and I'm going to calculate it here. P1 V1 T1 equals P2 V2 T2, right? And what do we got? We got 101.3 kilopascals. We got 750 milliliters. We got T1 is 298 kelvins. We know our P2 is our unknown. Volume did not change at all. And then T2 is 273 kelvins, right? So I'm going to leave some space over here and then say P1 V1 over T1 is equal to P2 V2 over T2. Now, you can do something interesting here. The volumes are the same, isn't it? So you can actually cross them out, right? And then what do we notice, right? If you haven't caught on to it before, it's pressure over temperature equals pressure over temperature, right? P1 over T1 equals P2 over T2. All right, so if that's the case, then what happens? We got to set up the problem where we want P2 to equal, P2 here is equal to, what's on the left side? P1 over T1. And then what are we doing with the T2? You're multiplying over to the other side, right? Now let's plug in our values. P1 is 101.3 kilopascals. Don't forget to write units because it's going to tell us if we're doing things right or wrong. T2 is 273 kelvins. Be careful that you don't plug in the wrong temperature. All over 298 kelvins. Okay, and that should give us a value of, do I have a value? Nope, actually, because, what does it say? Show a numerical setup. Okay, so in the end, Mr. Kim screwed up. They don't want the answer. In fact, if you write the answer without this, you'd be wrong. So P2, your answer is actually this, right? So that's all they're asking. Okay, so I'm not saying that if you write the answer, they're going to mark it wrong. What I'm saying is that some of you guys who take a calculator, punch it in, and just only write the answer down, then you'll get it wrong. If you do all this work and also put in the answer, that's acceptable as long as you circled the expression, which is what they're asking for, okay? All right, let's keep continuing to number 63. All right, oh no, this is organic, right? Let's see. I know we kind of started organic in period 1 class today, but let's see if we can figure this out. Number 63, identify the element in these 3 compounds that allows them to be classified as organic compounds. Guys, this is just a definition, right? What you guys remember? Organic, we are organic. We are what based organisms? We are carbon based, right? So that's it. It says identify the element, right? So literally all you have to write is the word carbon, like so. 64, identify the class of organic compounds to which compound 1 belongs. Compound 1 is a propylbutanoate, right? So ready? That's the key, the ending, okay? So let's go to organic molecules and go to the list right here. And then what we're going to do is we're going to look for something that has O8, okay? O8. And I'm scrolling up and down and look at this. Noate is right here, right? So this is the same thing as this, right? You're looking for the ending. And if you look through those, you'll know this is the only 2 that has the same ending, right? Which means what? This is how do we know class is? Class of compound is the first column. So therefore, this would be an ester. So you would write ester for 64. All right, let's continue. Identify the class of organic compound. Oh, no, we did this one, right? 64, yes. Write the chemical name for compound number 2. All right, so let's figure out how to name this guy, right? So what's the key here? Key here is to look for certain things. I see this carbon with an O on top and an OH to the right. So let's go see if we can find something that looks like that. I'm going to go to this column here and then start looking through. And I didn't go far before I found carbon with a double bond O on top and OH on the right. So here it is, right? So now what is it saying? It's set to name it, right? So it's set to name it. Right? Write the name for compound 2. Let's go. So all you have to do is go try to figure out how to decipher this name, right? So go all the way over here, right? It's an anoic acid is the ending. And let's look at the prefix prop. If you go up here, what does prop tell you? Prop tells you 3 carbons, right? So let's go double check that in this organic acid, I see 1, I see 2, and I see 3 carbons. So all we have to do is count the number of carbons right up to the carbon under the double bonded O. So let's go ahead and do that. I got myself 1, 2, and no, honestly, wait a minute. It's the same exact example, right? It can't get any easier. So this one, literally, what's the name? It's propanoic acid, okay? So this one, they literally gave it to you, right? So it's propanoic acid. Cannot get any easier than this, folks. All right, let's go to 66, part C. Okay. The periodic table elements has changed over 150 years. During this time, many elements have been added. So discovered elements 113, 115, 117, and 118 in period 7 were named in 2016. Their official names have been approved by the International IUPAC, right? Remember I talked about IUPAC? I had no idea what they were. So International Union for Pretty Awesome Chem. It's actually pure and applied chemistry. The table below lists the names, symbols, and top numbers. All right, let's go. Number 66, identify the element in this table that is located in the periodic table of elements in the group classified as noble gases. What's noble gas, right? It's the last group, right? So let's go. Let's go to our periodic table, right? And right here, let's go. Noble gas is group 18. Who's that? 118. So it's that easy, right? So 118. So therefore, it's oganesson. So you could write oganesson. Or if you don't want to screw that up like me, you could also write, I think you can write, they gave it to you, right? Symbol, OG. You could write OG, right? So instead of this, or you could just write OG and it's also acceptable. 67, explain in terms of valence electrons why the elements neonium and tennessine would be expected to differ in their chemical properties. Now, guys, this has nothing to do with this problem. This has everything to do with what these guys are, right? So what do we know? We know that the they have, right? Why do they act differently, right? They have different numbers of valence electrons. Right now, this is literally just a definition of why different elements from different groups have different chemical properties. Okay, I think that's the end of the period 8. So what I'm going to do is I'm going to pause right here and continue this at a later time. So stand by. Okay, folks, that was number 67, I believe. I'm back. Number 68, let's go talk about this question. Describe the general trend in first ionization energy values as the 5 elements above moscovium in group 15 on the periodic table of the elements are considered in their order of increasing atomic number. Now, this may sound really complicated, but it's not. In fact, this has absolutely nothing to do with this problem. It's just asking you a general trend in atomic theory, right? It's asking you what happens to the ionization energy moving down, right? From top to bottom, right? Because it says what? Increasing atomic number means you're going down, right? In a group. Now, I don't know if the atomic ionization energies are stated here, right? On 113, right? And it isn't, right? And that seems like it's a problem, right? That's been omitted, right? But that's okay because all you have to know is know it. You can solve it 2 different ways. One way is to know is that as you go down, what happened to radius? The atoms get larger, right? As you go down. So what does that mean? That means the electrons are subsequently further out away from nucleus. And remember the example we used in class back in October is if you have electrons further away, that's easier for somebody to grab and remove. So therefore, we know that as the radius gets larger, the ionization energy starts to get less and less and less, right? Because ionization energy trend is opposite that of the radius trend, right? The other way to solve this is to pick a representative group and just look at the trend, right? So we can even go back to a halogen and take a look. So fluorine, number 9, and then let's look at iodine, 53, right? So if you look at number 9, right, what do we notice? The ionization energy, right, for number 9 is 1681. What happens when you get down to 53? When you go down to 53, you notice ionization energy is 1008. So what do we notice? It went down, right? So that's literally the only thing you need to talk about, right? So they said when you go down, right, I say ionization energy gets smaller as you move down a group or a family. Okay? And that's that. Okay? So let's go to 69. 69. State in terms of protons why tennessine is listed before oganesson in period 7 on the periodic table of the elements. Tennessine, right? Tennessine is 117 and 118, right? Well, again, this has nothing to do with this problem. It has everything to do with why are some things listed before, right, on a periodic table going this way? Well, because they're arranged in their what? Increasing atomic numbers, right? So elements in the periodic table are arranged in order of increasing atomic numbers. And then what are the two that I can't remember the name of? 117 is what? Tennessine, TS, has one less proton than OG. Okay, so that's 69. Let's go to 70. Hydrogen gas is needed for many industrial chemical reactions. An equilibrium system that includes the use of catalysts produces hydrogen from methane and steam as shown in the equation below. This looks overly complicated. So again, don't panic, just take a look at it. Another equilibrium, so if you look at this equation, you see that, and I notice a couple of things. I see an energy on the reactant side. So what does that mean? That means it's what? Energy is a reactant. Energy is a reactant. That means it's an endothermic reaction, right? Okay. Another equilibrium system produces hydrogen as a representation by equation 2 below. And then what do we know about this one? Energy is now on the product side, so we know this is exothermic. I don't know if I need that information, but I'm just taking a note of it. Number 70, compare the rate of the forward reaction to the rate of the reverse reaction for equilibrium system. At equilibrium, right? I mean, how many times do I have to say the word equal, right? So what does it tell about the two rates going forward and reverse? If it's at equilibrium, it's the same. The two rates are the same. You don't have to say why. Literally, it says equilibrium. Number 71, state how the equilibrium shifts when the temperature of the equilibrium system at equilibrium represented by equation 1 is increased. So if you increase temperature, what are you doing? You're adding heat, right? So let's go to equation number 1. Equation number 1 is an endothermic reaction, which means you're adding more heat, or you're adding reactants. If you add more ingredients, then what's going to happen? It's going to end up going more forward, right? So the equilibrium shifts to the right, or you could also say products. Okay, once again, when you raise temperature, you're adding heat, but in equation 1, heat happens to be on the reactant side, and therefore adding more reactant makes it go towards the product. So it's going to the right or the product side. Okay, 72. State in terms of activation energy why the catalyst increased the rate of forward reaction represented in equation 1. It's again, this has nothing to do with it. It's just asking you to define catalyst, right? So what is it? Catalyst lowers the activation energy or you could also write catalyst provides an alternate pathway. Either one is acceptable. That's the correct answer. Number 73. On the labeled axes in your answer booklet, draw a potential energy diagram for the forward reaction represented in equation 2. Let's look at equation number 2, right? Equation number 2 is an exothermic reaction going forwards, right? So again, this is something that you just have to remember, right? Exo, endo, right? Exothermic reaction looks like this. Endothermic reaction looks like that. So that's the correct answer, right? Because equation number two going forward, right, is exothermic. So we're going to go ahead and draw an exothermic graph. Looks like that. Let's go to 74. The diagram labeled, oh, what is this? It is a voltaic cell. Right, you don't need to do this on the actual test, but I've just got excited because you guys know how to answer this, right? So, number 74, state the form of energy that is converted to electrical energy. Dude, there's only two energies that are the definition. One is what? Electrical energy and chemical energy, right? So that's it, just chemical energy. Again, this is literally definition question. Number 75. Identify one metal from table J that is more easily oxidized than copper, and less easily oxidized than iron. So let's go. So table J, if you remember correctly, it's oxidation and reduction like this, right? So more easily oxidized mean that higher than copper and lower than iron, right? Right, so let's go look for copper right here. Let's go to table J. Look for copper. Copper's right here, right? So identify one metal from table J that is more easily oxidized than copper, which is anybody above copper, and less easily oxidized than iron. Let's look for iron. Iron is here, like that. So the answer is any one of these, right? So you only need to write one, right? Except be careful, right? Right? So you can write any one. So cobalt, nickel, tin, what else? Lead. Now, some of you wrote this, but that's wrong. Why? Because what did the problem say? One metal, right? That's not a metal. So your answer could be any one of these four. Okay, you don't have to write all of them. 76, state the purpose of salt bridge. Well, what does salt bridge do? It's a definition. If you remember the definition of salt bridge, right? Salt bridge allows ions to travel through, or more specifically, or you can write that salt bridge allows an ion to travel in reverse of current in wire. Okay? But that should be good enough. 77. Write a balanced equation for the half reaction that occurs at the copper half cell. Let's take a look at what's going on in copper. Copper is going from here to there. So writing that out, what do you got? Cu2 plus Aq going to solid copper, right? So what is that? That's, you're forming more metal, right? So that's reduction, right? Not oxidation, right? Plus 2 electrons, right? Because we're going to need to balance the charges. And guess what? We're actually done, right? It's going to be copper, 2 plus aqueous, plus 2 electrons, giving us copper solid. Okay, that's 77. 78. In a lab investigation, 0.01 molar NaOH solution with a pH value of 12.0 is used to determine the molarity of HCl solution. What is this? Right? All right, so let's go. Let's start identifying these things. All right, so let's go. We got M, and that's base, so that's MB. The pH value of 12 is to determine the molarity. So this would be VA, right? And this is MB. I'm sorry, VB. Sorry about that. That'll be our VB. Now, why am I doing this? Because I'm pretty sure they're going to ask us to figure out the titration, right? See the color of the indicated litmus paper and the original NaOH. That's basic. That's base, right? So what do we know? Just go to the litmus paper, right? Some of you might have remembered this, right? But what do we know about this? If you go to acid base, there it is, litmus, right? Base is blue, right? So that's literally what you write, blue. Okay. 79. Determine the pH value of the solution that has hydronium ion concentration 100 times greater than the original NaOH solution, right? So there's two ways to solve it. The more involved way is what? NaOH. NaOH right here. So concentration of the NaOH equals 0.010 molar. But what did they say? It's 100 times more. So if you multiply this by 100, that's going to be equal to 0.01. I'm sorry, I screwed that up, right? That is going to be what? 0.01 times 100 will be 1.0, right? Everybody okay? Because remember, it's 100 times more than the original, right? So let me erase this and make it a little bit more legible. It's 100 times more, right, than the original, which is right here, 0.010. So therefore, it's 0.010 times 100, which gives you this, right? So it's the negative log of 1.0. That's going to be your POH, okay? And what is that? I don't know if I actually did that. I have a calculator right here, right? Well, I mean, there really isn't much, is there, right? Because negative log of 1 is 0, right? So what are we talking about? Um, oh, so we have to be careful with this, guys, right? This one's a little bit more involved than what we thought. So essentially, in the end, I mean, it's not wrong what I did, right? But essentially, be careful. It's 0.01 molar times 100, and then the other thing is we can't do this because why? It's 100 times more greater. pH is greater. Okay, so all we have to do is we have to take a POH of this, right? So POH equals negative log of 0.01, which is 10 to the minus 2. But if you punch it into a calculator, you'll get 2 as a value. Okay, now you get a 2 as a value, and you remember pH is 14 minus that, right? That gives you 12, right? But this is not the answer because it's 10 times, hold on a second. What was that? Yep, he did. All right, so it's 10 times more than that, right? So if it's 10 times more concentrated, it's more acidic. That means which way is pH going? It's going down. So if you haven't figured that out in class, remember every single time pH changes by 1, it's base 10. So it's going to be down 100 times lower would be down 2 clicks in the pH meter, which would give you a pH of 10. Okay? So the answer would be 10. Let's try to finish this up. I know ninth period is over now. All right, so let's go. Determine the molarity of the HCl solution using the titration data. This is literally what I was setting up for, right? So we need some space, so let's set that up. So MAVA equals MBVB, right? And what happened? Determine the molarity of HCl. So that's our unknown, right? Our VA is oh, and I messed that up too, right, guys? Why don't you say something? That's base, right? Right. All right, so must pitch okay. Oh no, I got it right. Guys, why don't you stop me? Right? It's 10 milliliter of this. This is what I was pointing to, right? So VA is 10.0 milliliters. MB is 0.010 molar. VB is 20 milliliters. And let's set up the problem. It's MAVA equals MBVB, right? So MA is equal to MBVB divided by MA. That's going to be 0.010 molar times BB is 20.0 milliliters all over 10.0 milliliters. And what does this come out to? That is same as 0.010 molar times 2, isn't it, right? So you don't need a calculator for this, do we? Right? That's your answer, right? So we're just going to transfer that right over here. That was for number what? 81. Oh, look at this. Remember what I told you? Cross things out and I didn't. That's why I skipped number 80. So I'm going to write down for 81. Right? But let's go to 80 because we missed it. Identify positive ion in the original. Like, this is the third FRQ question, and this is the same exact question they asked 3 times in a row, right? Who's the positive ion? It's the H plus, right? Right. So therefore, you just literally write that, right? Do you think it's important for you to know how to do this? I think so, right? 82. Spacecraft sometimes use nuclear power source to produce electricity from the heat released with decay of radioisotopes. Two isotopes have been used in the nuclear resource are plutonium-238 and americium-241. Both the Pu-238-241 emit alpha radiation and gamma radiation. The half-life of AM-241, they gave us the half-life. This is important. Why? I'll tell you that in a second. The other source of electrical energy for assumption of solar panels matters. Determine the fraction of the AM-241 remaining from original sample after this many years, right? Now, the first thing that a student might do is go to the table of half-lives, right? Right? The half-lives. Except when you go here, you're going to look all through this and you're not going to see americium-241. Why is that? Sometimes they can do that. They can do that as long as they give you the half-life in the body of the problem right here, right? So what does that mean? 432.7 year is per 1 half-life, right? So what does that mean? That means 865. We got to figure out how many half-lives, right? So it's 865.4 years, right? You're going to divide by, right? 432.7 years is for 1 half-life. What does that get you? That gives you 865.4 divided by 432.7. That gives me exactly 2 half-lives, right? What does that mean? That means you take a bite twice, right? So let's go. You start with 1, after one half-life, you end up with half. After the second half-life, you have half of half, which is quarter. That's your answer, right? So the answer is 1/4. 83. Compare the penetrating part of the alpha particles penetrating part of the gamma radiation, okay? So essentially, it goes from weak to strong, and the order is alpha, then beta, then gamma, okay? So you just have to memorize this, okay? So alpha particle has higher penetrating, I'm sorry, not higher, lower, right? Power than gamma particle, right? The only way is you just have to memorize this for this question, right? Right? So that's that. 84, right? Hey, check it out. Do I even need to read the questions? I don't. I know how to do this, right? So how does that go? You got 238 on the left side of this arrow. So we got 4 on the other side. So 4 plus what gives you 238? 234, right? What about on the bottom? You got a 94 on the left side. 2 plus what gives you 94? 92. And do you remember how we found the identity of the guy, right? If you don't remember, go look up helium, see what its atomic number is. Plutonium, look up its atomic number, and you realize it's the atomic number that's the bottom, right? So all you have to do is go look for 92, right? And 92 is right here, right? That's 92. That's uranium, and we're done. Right? Look at that. I didn't even have to read the question. Number 85. Compare the energy released by radioactive decay of 1 kilogram plutonium in this nuclear power source to energy released by 1 kilogram of chemical reactants. Okay. All right. Do I even have to explain this? Nuclear versus chemical. Which is more destructive, right? Right? So that's it. Nuclear is more energy. That's literally all you have to say. Okay? And that's it. That's how easy this section is. I hope this was helpful, and good luck studying for your Regents.